Okay, cool. Welcome back. Goal for today is wrapping up homework 4, seeing if there's any like lingering questions or like errors or things that we can work through today. Turn it in tomorrow is the 14th, and then I'll push off the deadline for project 4 because on Friday I won't be here. We won't have class for Friday. So take the day off. You can either work on the project or just take a break for a minute, like take a breath, and then we've got some time because project 4 is the last required assignment submission. Then homework 4 and 5, those are extra credit, or you can go back and revise any of the modules 1 through 4 work, and we can work on those. But that's the plan for the rest of this week and then into next week. And then we finally get that break that is 4 weeks too late, but it's here, it's coming. So no class Friday, and we'll wrap up module 4 today, at least hopefully. Wrap up module 4 homework today. Anything coming up? Working on anything interesting or cool? Questions? Last part? Yeah, like so here we're taking, so linear regression is called linear regression not because it's always a straight line, but because it's always a linear algebra problem. So that's like the big reveal, right? But if we want, I could take a look. We could just go through. Usually first step is just what kind of data am I trying to fit? What does it look like? How do I get it? How do I get Python to understand what it is? I like to always look at the raw file, like just the text that's inside the data. So head is a great command to look at that. It gives me the first 10 lines of the text file. And I can see time and stress. I don't need that first row, but I do want those 2 columns, and they're separated by a comma. So that gives me a lot of the information that I need to tell Python, hey, load this text into a NumPy array. It's in this location. Skip the first row because I don't want to try to load in the heading titles, and then delimit the file. So the file is delimited, which means like separated, each value is separated by a comma. Then I get a nice 2 by 22, 24 array, something like that. And I can turn that into like time and stress. So T and S are my 2 values. Let's just make sure those look the way that they're supposed to. T comma S. Do some squares, connect them with lines. And let's get rid of the lines. I don't like them. So T and S, it looks like a curve. If I scroll back up, kind of looks like that curve. It goes from 0 to 600, starts somewhere upper 30s, goes down to lower 30s. Seems like it's the right data loaded in there. Let's get rid of I'm just trying to delete this, start from scratch. Yep. Get rid of that. So what I want to do is take this function, spectacle, try and take this function and turn it into a least squares fit. So I'm going to say sigma of my function is e to the negative t 0 over 1.78, e to the negative t1 over 1.78, all the way to like t21, like however many points in time I have. Same thing here, like e to the negative t over t1, t0 over 11, t1 over 11. I can spell. So I'm setting up like this set of problems, and what I'm doing is creating something where I'm over constraining the solution, where I have lots of stress values, because at every point in time I have a predicted stress, and they can't all be the same problem. So I have like 22 equations but only 5 unknowns. So instead of trying to satisfy all 22 equations, I'm going to create that least squares regression. So I can say z times that. So here's a, this is z, z times a minus that like sigma I, or like sigma, squared, trying to minimize it, or ZA equals that sigma. So in order to get it into a solvable form, I say Z transpose Z times A equals Z transpose times that, times those measured like stress values. And when I solve, if I solve this right-hand side problem, that's going to be the minimum of that, the error. It's going to minimize like distance between my function and the measured values. So that means I need a Z function. t over 1.78 negative t over 11 np.exp negative t over 53. Is that right? Yep. Keep forgetting these brackets. And just keep the format the same. I'm going to say t times 0. And when I look at this, I'll print it out. Kind of looks a little ugly, so let's see if we can. How many are there? 1, 2, 3, 4, 5. So looking at like the Z matrix that I get out of it, kind of getting it all into one format. At time 0, e to the 0 is all 1s, so the first row is all 1s. And then as time moves on, that last column is always a 1 because it's just giving me like some kind of offset parameter, like some constant. And then all these other ones. Here for the smallest time constant, it goes to 0 the quickest, and then the longest time constant goes to 0 the slowest. So I have like a negative t to the something. And if I plug in that the solution that I was looking for, like Z transpose Z, Z transpose S, then I get 5 outputs. And each one of these is the coefficient for that function that I was looking for, like that e to the negative t over 1.4, and then t over 11, t over 53, t over 400 something. And if this is enough, like if you're just looking for a function, like find those coefficients, and it looks right, then this is good enough, right? Because we can compare z times that a and say, look, I was looking for those coefficients, and sure enough, this curve matches my data. Everything's good. But if someone's like, well, how do you know that that's a good fit? Or like, what's your R squared value? What's the stats behind it? Stats Models is a nice library that does the same solution for you, and it's the same kind of setup that we just did, but it gives you a lot more information. Have you seen this before? Have I showed you this yet? Stats Models. So we have SM, and then what do I want to do? SM dot. Oof, I always forget the process though, because you create the model, then you fit the model. Yeah, so we say model is this. So our model is the Z matrix that we made. So that's only a function of the independent variable, and the things that we observed are the S values. And once we define the model, now we can say, okay, take that ordinary least squares model, that's what OLS stands for, and do a fit. So model.fit is going to solve that least squares regression problem, which is the same thing that we just did here. And we'll get the same exact values, that 1.9, 3.3. So it gave us the same result, that least squares, the ordinary least squares regression. But the nice part is now we can say in that results, take a look at the summary. Oh yeah. And now it gives us all the stats information plus 10 extra values that maybe we need, maybe we don't, but we can kind of bury all the naysayers with data in this case. Like, all right, what's your R squared value? It's 99.3%. My adjusted R squared is 99.2%. I had 22 observations, and degrees of freedom were 4 for this model. And there were 17 DF residuals. I used a non-robust covariance type, right? Like all of our different like statistics for these kind of least squares regression fitting. But we still get that same array. A is still exactly what we had gotten before. But let's say, so like since I have all these coefficients, like I have a function defined, I should be able to evaluate that function at any point in time. Like I should be able to look at time 0 or time 1. And I can do that. I can let me take this like Z array, and instead of saying that it's T, like the actual values of T, I'll turn it into a function of T. So if I plug in a value of T, it should give me a Z array, and then I can multiply that by my coefficients, and now I've got a solution like that. Oh yeah, so I want to say Z function. So ZF of, and I do need to say that it's an array. So at time 0 times A, my initial stress is 39 megapascal. Or if I want to say like, well, what happened at 10 seconds? At 10 seconds, the stress was 34.9 megapascal. And that kind of matches up with here, right there, like 35 megapascal. Or you can plug in like all those different values of like T function and say, all right, let me evaluate this from 0 to 600 with 51 steps along the way and get like a nice smooth curve. Or 500, I can use as many steps as I want. Because at this point, it's just a function that I can evaluate anywhere. Gives me a whole bunch of values, so I don't want all those things. T function, the f of t function times a. Now I've got like a nice smooth curve because it's evaluated 500 different data points from 0 to 600. All sorts of cool stuff that we can do once we get a nice fit to our data. But if you're building out that Z matrix, the stats models, it's a nice way to get a lot of good information from your fit. Oh, okay. Then from there, like, if you use the same like 3 lines, like model and both OLS, in this case it would be Catholic in US, Z, and then result model that would give you all same data, just yeah, dot API. Oh, okay. That's right. Which part are you working through? Okay. I'm working through. Yeah. And that one, I was surprised. That was the first one we tried like ChatGPT to transform latex into an array. I was surprised at how well it did recognize and get us like the right code. It was pretty close. The coding is pretty accurate. Yeah, yeah. Like if you're just looking for very specific. Yeah, exactly. Yeah, like these pictures like this. Yeah. And you can help, like if you like give it definition of what you're looking for, as well as what you're trying to do. And also it works for like older, so you memorize stuff is great. But if you're trying to do there's newer libraries that are like, hey, can you show me how to, and then I'll show you something that's way out of date. Yeah. It is good at interpreting errors. Yeah. That'd be kind of cool if you had like when you get an error, like filter it. Yeah. Like show you just a little bit of the error, but then also the GPT response. Yeah. Like this is what we think happened. Yeah. Okay. Yeah, yeah. Yeah. So in that case, if you look at the first row of that matrix, yeah, that left hand side, 6x6 matrix, the very first row in the very first column is 0. And Gauss elimination takes that number and divides it by every number below it. So if you do that would be full division. Like that would relabel P1 to P2 in the output. So if you take row 1, row 2 and switch them, now all your X tags are still the same. No issues. Yeah, so yeah, you do like in general, like the solver, now that's all would be partial coding, so we'll do that in the background. I was going to say that yeah. Yeah. Yeah, that one, last time we did this data set in, we used pandas. Being like 2. Yeah. That one is a little better because your formatting needs Oh, coming down. Let's take a look at this. Do I have this? Ah. Yeah, anyway. Yeah, we're out of time, but thanks a lot. And then, did you want to meet? Oh, we could walk up to my office. I'll just close up all this stuff. All right. Thanks for joining.